The birth, death, and physics of the universe are big questions still awaiting big answers. Also, what is that annoying hum in New Mexico? In case you're wondering, this is a new episode from our series Great Mysteries, and today we're going to discuss many of these intriguing questions that we still don't have a definitive answer to. And this episode is going to be the last episode of the series, and let me tell you about the questions we're going to discuss today. We're going to start talking about mysteries related to natural forces on our planet and a little beyond as well. Let me tell you about the questions we're going to discuss. We're going to start with a very intriguing question. How did the universe begin? And then we're going to continue with even more interesting questions. What is gravity? Where is the antimatter? What's the origin of powerful cosmic rays? Why is the sun's corona so hot? Do sunspots affect Earth's climate? How was the moon formed? Does Earth hum? What is the nature of Earth's core? What causes the flips in Earth's magnetic field? What was the beginning of life on Earth? What triggers an earthquake? Why do rocks slide across Death Valley? What made the Eye of the Sahara? How do tornadoes form? What causes rogue waves? What is ball lightning? Is there life on other planets? Is it possible to travel through time? Do we live in a multiverse? What is dark energy? Will we ever find the theory of everything? So these are the questions we're going to discuss in today's episode related to natural forces. So get ready for one last ride into the world of great mysteries. This is your host, Danny, and this is English Plus Podcast. We're going to start with our first question. How did the universe begin? It is a well-known anecdote. A famous scientist is lecturing on astronomy when a woman in the audience stands and contradicts him. The universe, she says, rests on the back of a giant turtle. But what does that turtle stand on? He asks smugly. Very clever, young man, she replies. But it's turtles all the way down. And here, I'm not making fun of this conversation, not at all. But this question is as old as time itself. We want to know how this world we live in, how did this universe all begin? And we started with ideas that might sound stupid to us in our day, but it was not stupid back then. Because there must be a reason, there must be a kind of explanation. And you might have heard of all the strange explanations, not only the turtle thing, but a lot of other strange explanations. But this is us. We are curious. We cannot settle for no answer. We have to come up with an answer, no matter how stupid that answer might sound. And yes, today, every man and woman in this world knows that the universe is not resting on the back of a giant turtle, and it's not turtles all the way down. But do we really know how the universe began? Well, I'm not so sure of that. Cosmologists attempting to understand the events at the beginning of time find themselves asking similarly circular answers, although there's a general but far from universal consensus on what occurred in the universe beginning a few moments after the Big Bang. Profound scientific and philosophical barriers stand between us and understanding what came before that, which is the transition from nothing to something. A standard timeline looks like this. About 13.8 billion years ago, just after the universe began, it was unimaginably tiny, hot, and dense. Gravity, electromagnetism, and the strong and weak forces were unified. For a short time, the universe expanded at extraordinary speeds in a period of cosmic inflation. The basic forces separated from one another. As the universe cooled in the next thousands of years, particles formed and then atoms, and the universe began to look more like we know it now, with matter condensing into stars and planets. The scenario still questions what existed before the Big Bang. No information can reach us from those primordial moments, but some physicists have put forth a partial answer. According to quantum physics, even in a perfect vacuum, random fluctuations can produce matter and energy. Perhaps the universe simply popped into being. Critics respond to this answer assumes that physical laws already existed, a variation of the turtle analogy. It's physics all the way down. But do we have a clear answer? Absolutely not. We have absolutely no idea. I mean, even the Big Bang, we're not so sure about it, but we still have theories about the Big Bang and what has happened since the Big Bang. But even if we agree for one moment that we do know what has happened since the Big Bang, what actually happened before the Big Bang? Did it just happen? From nothing? I mean, we don't have anything like that in physics. We don't understand it yet. Maybe one day we will understand it. Maybe one day it won't be a mystery, but today it's still a mystery and one of the greatest mysteries ever. And that's why it is our very first question in today's episode. And this is not the last question. You know that we have a lot of questions, so don't go anywhere. Next, we're going to talk about gravity. I'll be right back. So what is gravity? To Sir Isaac Newton, gravity was a universal force acting on matter. Every particle of matter attracted every other particle, with the strength of the attraction drooping off quickly with distance. To Einstein, gravity was built into the fabric of space-time. A massive object causes space-time to curve around it, like a blanket under a bowling ball. To quantum physicists, gravity is one of the four fundamental forces of nature, along with electromagnetic force and the strong and weak forces of the atomic nucleus. All of these theories have experimental support and are internally consistent. Unfortunately, the last two are not consistent with each other. Einstein's theory predicts that accelerating bodies will produce gravitational waves. Well, these haven't been detected yet. Quantum theory predicts that gravity would be carried on particles. Just as the electromagnetic force is mediated by photons, gravity would be mediated by gravitons. These have not been detected yet either, nor have physicists been able to mathematically unify gravity with the other three forces. To add to the mystery, recent findings in cosmology are leading some physicists to question the basics. We may need to rewrite gravity's rules to explain our dark and accelerating universe. So, it might be a very simple question. What is gravity? Oh, gravity is very simple. Isaac Newton talked about it hundreds of years ago, but not really. We don't really know one of the basic things that we take for granted that enable us to stand firmly on the ground. Gravity. We think we know it, but we don't actually know it that well. It is still a mystery. And it is our second mystery in today's episode, and it's not the last. Next, we're going to talk about the antimatter, or the antimatter, for that matter, it doesn't matter. But it's the antimatter we're going to talk about next, so don't go anywhere. I'll be right back. So where is this antimatter, or antimatter? In the existing years of the early 20th century, when physics was redrawing our picture of matter, scientists realized that every particle must have an antiparticle, one with the same mass but an opposite charge. Thus, electrons, which are negatively charged, must be matched by positrons, which are positively charged. Protons, which are positively charged, must have a counterpart in antiprotons, which are negatively charged. Indeed, experiments in accelerators can produce exactly these particles in large quantities. The matter and antimatter particles must be kept apart, however, or they will annihilate each other in a burst of energy. Physics also states that during the Big Bang, equal amounts of matter and antimatter must have been created, and there's the rub. Though we have detected small amounts of antiparticles in space, virtually everything we see is made of matter. So where did the antimatter go? The missing antimatter remains one of the fundamental puzzles of cosmology. One explanation is that particles and antiparticles may differ just slightly in their rate of decay. Even a tiny variation over time could lead to today's asymmetry. Experiments at Geneva's Large Hadron Collider may shed some light on that problem. But do we have an answer? Of course not. That's why it is another mystery, and that's why you're hearing about this mystery in today's episode in our Great Mystery series. But stick around, don't go anywhere, because next we're going to talk about cosmic rays. I'll be right back. So cosmic rays, huh? What is the origin of those powerful cosmic rays? Now stand outside, and about once a second, you'll be hit by a cosmic ray. Don't you feel it? Well, that's normal because each ray is a subatomic particle, typically a proton. Observed about 100 years, cosmic rays rain down into Earth's atmosphere at high speeds from all directions. Some come from the sun, but most shoot in from distant, unknown sources. A few are so energetic that they travel at almost the speed of light. Scientists have long wondered what kind of blast could propel a particle to such speeds. A particle can't simply be tracked back to its source because cosmic rays curve along the magnetic fields that permeate interstellar space and surround our planet and so on and so forth. So simply put, we cannot know where they came from. Recently, however, researchers have found some evidence linking the ultra-high energy rays to magnetic fields around supernova remnants. Apparently, some charged particles trapped in these fields accelerate around and around through the supernova's shock wave, picking up speed and eventually shooting out like a bullet into space. In February 2013, astronomers announced that the Fermi Gamma Ray Space Telescope had detected gamma radiation characteristic of these interactions around two supernova remnants. That's not exactly proof, but it is our best lead yet for the source of these mystery particles. So whenever you're outside, you're being constantly hit with these cosmic rays, and unfortunately, we have no idea where they came from. So that was about these cosmic rays, but don't go anywhere because next we're going to talk about the sun's corona. And I'm not talking about coronavirus, all right? So don't mix these two things up. Although some people say that the coronavirus is still a mystery, but I guess it's a mystery that will be solved very soon. But anyway, let's stick to the sun's corona. That's what we're going to talk about next, so don't go anywhere. I'll be right back. So why is the sun's corona so hot? At its core, the sun registers temperatures of 16 million Kelvin, which is about 30 million degrees Fahrenheit. An unimaginably intense heat able to fuse atoms and release the energy that sustains Earth. Temperatures drop as you move out from the core, reaching about 5,800 Kelvin or 10,000 degrees Fahrenheit at the sun's visible surface. Then, inexplicably, the heat shoots up again in the sun's wispy outer atmosphere, which we call its corona, to between 1 million and 5 million Kelvin or 2 million to 9 million degrees Fahrenheit. This extreme heat has mystified astronomers for years. New and extremely sensitive telescopes are now providing clues to the reason for the heat. Two mechanisms might be at play. We've long known that magnetic fields twist through the sun, rising and dropping through sunspots and contributing to the star's bubbling, swirling chaos. It appears that these fields create waves known as magnetohydrodynamic waves that propel energy from within the sun into the corona. The hottest temperatures may come from a different magnetic motion. Lines of magnetic flux apparently twist themselves into tangled braids and then snap back into a simpler pattern, releasing so much energy that the corona may zing up to millions of degrees. But again, remember, that is just a theory. That is just a possible explanation. It might be true, might not, who knows? But that is a mystery, and that's why we have it in today's episode, one of our great mysteries. And it is definitely not the last mystery we're going to talk about, because next, we're going to talk about the effect of sunspots on Earth's climate. That's coming next. Don't go anywhere. I'll be right back. So, do sunspots affect Earth's climate? Now, before we jump to the easy question, yes or no, let's talk about it a little bit more, and then you can say whether it's a yes or a no, or most probably maybe. Before observers knew what sunspots were, they were tracking them. 19th century amateur astronomer Samuel Heinrich Schwabe, diligently recording the dark spots on the sun's surface every day for 17 years, recognized that the number of spots waxed and waned according to a regular 11-year cycle. Later, scientists learned that sunspots mark places where magnetic fields break through the sun's visible surface. When the sunspot cycle is at its peak, ultraviolet radiation increases and the sun is particularly stormy, erupting in solar flares that can disrupt electrical transmissions here on Earth. The theory that sunspots might do more than that they could affect Earth's weather, for instance, was long derided as a tin hat notion. However, some researchers now believe there may be truth to the idea. A period of extremely low sunspot activity from 1645 and 1715, known as the Maunder Minimum, is linked to a frigid period on Earth when temperatures averaged between 2 and 3 degrees Fahrenheit below normal. Studies of tree rings also support a connection between solar cycles and climate. Earth's climate is so complex, and its mechanisms still under study, however, so the jury is still out on the sunspot question. And after I told you about that, I don't think a simple yes and no answer will do. I guess it takes a little bit more than that. It is still a mystery. And that's why we have it in today's episode. But that's not the last mystery we're going to talk about today. Next, we're going to talk about the moon. How was the moon formed? That's coming next. Don't go anywhere. I'll be right back. So how was the moon formed? The moon is the Earth's only satellite. We don't have any other, like other planets where they have a lot. And by the way, you're going to learn a lot about that in our upcoming series, Beyond Earth. So stay tuned. But anyway, let's get back to the moon and how the moon was formed. The moon, which is, as we said, the Earth's only satellite, is a familiar companion, but one whose origins are still murky. Early theories included the idea that it formed at the same time as Earth from the debris of the early solar system, or that the Earth captured the wandering moon as it floated past, but studies of moon rocks and the physics of such a capture make both ideas implausible. The current model of the moon's origin is now the most widely accepted. But when we say accepted, we don't say that it is final. We might still get another answer, but let's talk about this current model of the moon's origin. Early in Earth's existence, about 4.5 billion years ago, a giant object the size of Mars struck Earth a glancing but titanic blow. Great chunks of Earth's crust and mantle were ejected into space, emerging with parts of the impacting body in a molten disk that coalesced to form the moon. This theory is supported by the overall composition of the moon and the mathematics of the spin of both Earth and its satellite. Well, while this is the most accepted theory, but it's still a mystery. Recent studies of moon rocks have cast some doubts on this idea. If lunar rocks are a mixture of Earth and impactor, their chemical composition should reflect this. Instead, they seem to be chemically identical only to Earth rocks. Scientists aren't discarding the impact idea just yet, but they may have to go back to the drawing board when describing just how the debris became the moon. Still a mystery. We still don't know for sure how the moon was formed. But that's not our last mystery for today's episode. We still have more. And next, we're going to talk about the humming of the Earth. Does Earth hum? That's what we're going to find out about next. So don't go anywhere. I'll be right back. The sound is described as irritating, a low, rumbling noise like a distant diesel engine. People in locations ranging from Auckland, New Zealand to Beaufort, Ireland have reported hearing it. In most places, obvious suspects such as machinery or traffic noise have been ruled out as a source. One of the best-known hums is the one reported in Taos, New Mexico, beginning in the early 1990s. So annoyed were the locals that they petitioned the New Mexico congressional delegation for an investigation, and they got one. A team from the University of New Mexico traveled to Taos, interviewed its residents, and set up sensitive microphones. They determined that about 2% of locals heard the noise, which is a low-frequency E-flat rumble. They ruled out resonance from the power grid and vibrations from distant military installations. Their own microphones did not pick it up. They concluded, we are left with a mystery. There are no known acoustic signals that might account for the hum. Many explanations for the hums have been suggested. One of them is tinnitus or tinnitus, which is ringing in the ears, but that might not be the case because tinnitus is typically high-pitched. There was also another explanation, which is machinery, which is still not found. maybe some invisible machinery, maybe some secret machinery somewhere nobody knows about. And some other explanations went on to say that it's simply hypersensitivity to ordinary background noise. But is it the Earth's hum? Maybe it is. Maybe some people are that sensitive because the Earth does make noise, but that is far below the limits of human hearings. The sounds include rumbles from ocean waves and deep crackles from lightning. Some can be heard with very low-frequency radio receivers, but not human ears. So maybe it is the Earth. Maybe some people have this kind of hypersensitivity to these sounds, but the mystery is, does Earth hum loud enough for people to hear it? That we still don't know. But don't you worry about that. Most of the time when you hear those hums, it's like coming from a nearby factory or some other source, some other man-made source, but it's definitely not the Earth's hum. But maybe some people hear it in certain places around the world where they have an acoustic advantage or something like that. I don't know. It's still a mystery, and it's not the last mystery in today's episode. Next, we're going to continue talking about the Earth, and we're going to talk about the Earth's core. Well, what is actually the nature of this Earth's core? That's coming next. Don't go anywhere. I'll be right back. Well, the Earth's core begins about 1,800 miles or 2,897 kilometers below us. But it is so inaccessible, it might as well be in another galaxy. Scientists have formed a rough idea of its nature by studying how seismic waves pass through the planet, gauging Earth's mass and density by how it interacts with other bodies, and digging into the planet's outer layers. Based on these measurements, scientists think the core is a metallic sphere about 2,200 miles or 3,541 kilometers in radius. Don't think it's small, it's kind of the size of Mars. It may consist of two layers, a solid iron alloy inner core and a liquid iron alloy outer core. Temperatures may reach 5,800 Kelvin or about 10,000 degrees Fahrenheit in the inner core. Heat emanating from the core is what powers our shifting tectonic plates. Questions remain. Some findings suggest the inner core hides an even smaller solid iron innermost core. Seismic measurements indicate that the inner core may rotate at a different speed from the rest of the Earth. Recent studies find more heat than expected rising from the core. Again, we don't know why. Scientist David Stevenson has semi-seriously suggested breaking open a crack in the planet and sending in a probe. Well, while that might be a good idea for movies, and I believe they made a movie or two about that, there's no doubt that many planetary scientists wish we could do just that. So, what's the nature of the Earth's core? We have an idea. But do we know for sure? Not at all. And it is right below us. It is that close, but so beyond our reach. For now, who knows? Maybe in the future we will figure out a way to go to the core. And then we know for sure what we can find in there. But that's another mystery in our series, and that's not the last one. What about magnetic fields? What causes the flips in Earth's magnetic fields? That's what we're going to find out about next, so don't go anywhere. I'll be right back. So what causes the flips in Earth's magnetic field? Earth's magnetic field, generated by currents within its liquid iron core, shields the planet like a vast umbrella from deadly cosmic radiation. In the 20th century, geologists studying magnetic patterns in seafloor rocks were surprised and a bit disturbed to learn that this basic planetary feature is capricious, changing its polarity at seemingly random intervals over the millennia. Magnetic north becomes south, becomes north, over and over again. On average, the field reverses every 200,000 years or so, but it has been 780,000 long years since the last flip. Although one recent study suggests it turned over briefly about 41,000 years ago during the last ice age. A reversal can take thousands of years, during which the field may weaken and multiple magnetic poles appear at various latitudes around the planet. We don't know what brings about these sporadic flips. Some computer models of the magnetic dynamo at Earth's core suggest that small instabilities in the field as it is generated can grow into complete reversals. The magnetic field is now about 10% weaker than when it was measured in the 19th century. Perhaps it is a sign of an upcoming reversal. Geoscientists say not to worry though. The process takes a very long time and should not seriously affect life on Earth, at least not in the few hundred years to come, even if it is happening right now. Yeah, we talked about what the magnetic field and the flip is, but what causes that flip in the Earth's magnetic field is still a mystery, and it's another mystery for our Great Mystery series, and it's not the last one. Today we have a lot of mysteries to talk about. Next, we're gonna talk about the beginning of life on Earth. What was the beginning of life on Earth? We're gonna answer this question next if we can, so don't go anywhere. I'll be right back. Sometime between 4 and 3.5 billion years ago, the young Earth crossed the threshold and became a living planet. How did the first forms of life appear in Earth's oceans? And of course, it was primitive. These are just organisms that took in energy and reproduced. How did that happen? Assuming that life arose from simple organic chemicals, two main schools of thought emerge. One suggests that the chemicals for life reached Earth from outer space. Scientists have found a surprising number of complex organic molecules in space. Spectral analysis of interstellar molecular clouds reveal organic chemicals such as sugars, and organic compounds have also been recovered from comets and meteorites. It is not unlikely, maybe even probable, that comets and other icy space debris smacking into Earth in its early years brought ready-made organic chemicals to the planet's surface. The other and more common school of thought has life arising from chemical reactions in the ocean. The famous Miller-Urey experiment of 1953, in which scientists energized a primordial soup with an electrical charge and saw the emergence of amino acids, showed that no special conditions were necessary for organic chemicals to form. Many variations of this hypothesis have been put forth, including organics arising in the warm waters near hydrothermal vents or else under the ice of frozen oceans. The next step is equally hard to decipher. How did organic chemicals organize themselves into a self-replicating system with proteins and nucleic acids working together? Many scientists believe that RNA, not DNA, was the earliest form of genetic code. Some experimenters have made RNA bases in the lab under conditions that might have occurred on the early Earth. And while we may find some reason in some of these explanations, most work on the origins of life still involves large quantities of speculation. So it is definitely still a mystery. But it's not the last one for today's episode. Next, we're going to talk about earthquakes. What triggers an earthquake? That's coming next. Don't go anywhere. I'll be right back. The earthquake that struck in 2011 off the east coast of Honshu, Japan's largest island, was a nightmare come to life. The magnitude 9 quake and resulting 97-foot-high or 30 meters tsunami killed more than 15,000 people and destroyed more than 300,000 buildings. No one predicted the quake because no one could. Scientists know the basic mechanism of earthquakes. Simply put, for earthquakes not related to a volcanic eruption, two blocks of earth sliding along the fault line build up energy from friction and then suddenly release it when a block overcomes the friction and jolts forward. The energy then moves in waves through the ground, shaking the surface. Many mysteries remain, however. Why, for instance, does the friction suddenly ease? Does the rock become molten along the fault or powdery like talc? Why are so many earthquakes minor when lab simulations predict they should be devastating? Pressure from water in reservoirs or wastewater injected into the ground during natural gas drilling seem to sometimes trigger quakes. But how? And are these quakes dangerous? Unfortunately, we don't have firm answers to these questions, and science is still at a loss to predict the next disaster. So what triggers an earthquake? We have an idea. But we don't know for sure, and obviously we cannot tell when the next big earthquake is going to happen. And that's why we still call it a disaster that cannot be averted in most cases. And it's a mystery, of course, and it's not the last one. The next one, we're going to talk about the rocks sliding across Death Valley. So don't go anywhere. I'll be right back. So the question is, why do rocks slide across Death Valley? The moving rocks of Racetrack Playa, which is a flat, dry lake bed in Death Valley National Park, have intrigued visitors for years. Though they've never been seen in action, rocks weighing up to 700 pounds or 318 kilograms have been found at the end of long tracks scraped out of the playa's desiccated surface. Some of these paths are up to 3,000 feet or 914 meters long. The rocks are not sliding downhill. In fact, most are traveling very slightly uphill. Nor can wind by itself move heavy boulders these distances. No human or animal tracks mark the delicate surface around the rocks trails. Researchers are hampered in finding answers by the limitations of working in Death Valley, which is a sensitive ecosystem that would be damaged by invasive installations. Most current theories involve a combination of wind and a slippery surface. Fierce winter blasts may give the rocks a boost over a surface temporarily softened into mud by Death Valley's rare rains. Or the rocks could be skating. Water might occasionally turn to ice under the boulders, erasing friction and allowing the wind to scoot them across the playa. Or both of these scenarios and more may apply at different times. Or maybe there's some other explanation that we still don't know about, but it is still a mystery and we don't have definitive answers. We just have theories. We just have explanations that might be right and might be wrong. And that's why it's a great mystery, and it's one of our mysteries in our Great Mystery series, and it's not the last one. Next, we're going to talk about the Eye of the Sahara. What made the Eye of the Sahara? That's coming next. Don't go anywhere. I'll be right back. Looking like a giant bull's eye for the interplanetary target practice, the Eye of the Sahara, or Richat structure, is a striking circular feature in Mauritania's Sahara. 30 miles or 48 kilometers across, the structure has rings within eroded rings and glows a pale blue in the dun-colored land. Some imaginative observers have seen a link between the eye's circular structure and that of Atlantis as described by Plato. In Critias, he claimed that the city was bounded by circular canals and belts of land. More sober heads have speculated that it is an impact crater, but research into its rocks doesn't support this. Current theories suggest that it is a purely geologic structure, a rocky dome worn down by time and the Sahara's harsh environment. Sedimentary rock in the center dates back to the late Proterozoic era, which is about 1 billion years ago. Quartzite rock, which is more resistant to erosion, forms the eye's circular ridges. The dome may have been created long ago by igneous rock pushing upward from beneath the surface. Today, it's a landmark for astronauts, clearly visible from space, and for non-astronauts from Google Earth, just check out Mauritania and you will see this Eye of the Sahara. Next, we're going to talk about tornadoes. We're going to ask the question, how do tornadoes form? So don't go anywhere. I'll be right back. When it comes to advanced notice about tornadoes, today we're more fortunate than the folks along the 219-mile or 468-kilometer path of 1925's tri-state tornado. 695 people died in that outbreak. Swathed in boiling clouds, the wide, fast-moving storm tore through towns and farms without warning. Only the last 60 years or so have meteorologists had the tools, notably Doppler radar, to spot the conditions that might breed a twister and to issue warnings to the public. Atmospheric science is extremely complex though, and scientists still don't know why some storms whip up tornadoes, and whether those twisters will be weak or strong. We have learned that the most violent tornadoes are born from intense thunderstorms known as supercells. For reasons not entirely clear, rising warm air under the storm begins to spin while higher, cooler air rushes downward. In some conditions, the spin turns into a funnel cloud. Tornado intensity is measured by the 6-degree enhanced Fujita scale, which is based on the damage caused. The storms vary widely in size, ranging from a couple hundred feet, which is about 61 meters across, to monsters more than 2 miles or 3 kilometers wide, such as the F4 that struck Hallam, Nebraska in 2004 and destroyed 95% of its buildings. Even with modern warning systems, the 2-day outbreak that included the Hallam tornado killed 385 people. So, yes, we know something about it, and fortunately we can predict it most of the time, but we still don't know exactly how these tornadoes form. And that is still a mystery, and it's not the last one in today's episode. We have more. Don't go anywhere. I'll be right back to talk about rogue waves. Cruise ship captains and oil rig roustabouts told the same story. On rare occasions, walls of water 10 stories high would sweep in from unexpected directions and smash windows and gear, if they were lucky, no more than that. Oceanographers used to scoff, citing studies that showed such waves could occur only once every 10,000 years. Extreme storm waves are now accepted as fact, thanks to improved documentation from ships, oil rigs, and satellites. In 1995, lasers on an offshore oil rig in the North Sea measured an upcoming wave at 85 feet or 26 meters. 2 cruise ships in 2001 lost their bridge windows to waves 98 feet or 30 meters high. Satellites controlled by the European Space Agency spotted 10 waves about 82 feet or 25 meters in just 3 weeks' time. Scientists now estimate that at any given moment, 10 rogue waves are roaring through some part of the ocean. Theories about what causes these monsters are tentative. The waves often occur in strong ocean currents, such as the Gulf Stream or the Agulhas Current off the coast of South Africa. They may grow when storm winds blow across the gain of these currents, shortening the waves' frequencies and building their heights. Other rogues may form when swells traveling in different directions meet, their waves and troughs reinforcing each other. But these are only theories or possible explanations, but these are not definitive answers to what causes rogue waves. And remember, scientists not a very long time ago didn't even believe in them, didn't even believe that 2 rogue waves would happen within the same 10,000 years. But now they believe that at any given time, 10 are roaring somewhere in the oceans at the same time. So things change and explanations change, and until then, it is still a mystery. Next, we're going to talk about ball lightning. What is ball lightning? That's coming next. Don't go anywhere. I'll be right back. Ball lightning, often seen but little studied, is a phenomenon that is so bizarre that some scientists think it's simply a hallucination. It typically, but not always, forms during a thunderstorm, appearing as a glowing ball of light ranging in size from tennis ball to basketball. Observers describe it bouncing along the ground or floating a few feet up, jerking back and forth, hissing or sizzling before exploding with a bang. It can float into houses through windows. Airplane passengers have seen ball lightning scoot down the aisle before disappearing out the back of the aircraft. Ball lightning also has been seen above active faults during earthquakes. Rarely is the phenomenon dangerous. But in one famous exception, 18th century German physicist Georg Reichmann was killed when ball lightning in his lab hit him in the head. Whatever it is, it's not lightning. Some researchers explain it as a burning silicon dust, bound into a glowing ball after a lightning strike. Others suggest that electrically charged particles accumulate on surfaces such as windows during a storm, building up an electric field that discharges as a ball. Experiments to recreate it have been only marginally successful. And before we even know how they are formed, we don't exactly know what they are. So it is still a mystery, and it's not the last for today's episode. We still have a few more mysteries before we wrap up not only today's episode, but the entire series. We're gonna talk next about life on other planets. So don't go anywhere. I'll be right back. So is there life on other planets? It's a big question, of course. But let's see how much we know about that. Many scientists invoke the Copernican principle to support their belief that life will be found on other planets. Named for the astronomer who proved that Earth does not hold a special place in the universe, it points out that our planet formed from common elements around a typical star, and there is no reason why others like it should not exist. Opposing this view is the so-called Fermi paradox. Supposedly, the great physicist responded to a discussion about intelligent alien life by asking simply, "So where is everybody?" But the question itself is a paradox, because we can't find them anywhere. We can't go anywhere to find them. So maybe they have the same situation like us. Maybe they're as intelligent or even a little bit more intelligent than us, but they still don't have the means to communicate, just as we don't. But anyway, whether we'll find intelligent life on other planets is still a big question, but finding life of some sort seems incredibly plausible. An avalanche of recent discoveries of extrasolar planets leads most astronomers to believe that it's only a matter of time before we find one with Earth-like climate, including water. On Earth, at least, liquid water is the universal solvent needed for biochemical reactions. Carbon, the backbone of amino acids, may be another requirement. The extreme conditions that might be found on some worlds are not necessarily a barrier to life, however. Extremophile bacteria have been found on Earth in boiling hot water and beneath Antarctic lakes. The fact that life can thrive at these extremes makes the sub-ice ocean of the moon Europa or the possible groundwater reserves on Mars promising nearby targets in the search for life. But unfortunately, we still don't know anything about that. But that's not the last mystery for today's episode. We still have a few more, so don't go anywhere. Next, we're going to talk about traveling through time. Is it possible? That's coming next, so don't go anywhere. I'll be right back. Could a human ever truly travel through time? Physicists say maybe, kind of, but not in the way you see in science fiction. That's definitely not the case. Most time travel scenarios derive from the more extreme implications of Einstein's theories of relativity. Time is not separate or absolute as part of the space-time continuum. It slows for very massive or very fast objects. A 20-year-old woman boarding a spaceship that travels for 5 years at close to the speed of light could return to an Earth on which 50 years have passed. She has effectively traveled 45 years into the future. The same effect would apply if she visited an extremely massive object such as a neutron star. Wormholes are another theoretical time portal. Certain kinds of black holes just might form a tunnel through space and time. If they exist, however, wormholes would require an exotic species of anti-gravitating matter to stay open, and almost certainly would destroy anything traveling through. These radical methods require vast amounts of energy, far more than we can currently harness, and work only for travel into the future. Travel into the past is a different animal. Even in theory, it seems to be impossible. Then there's the often quoted but very real grandfather paradox. If you go back in time and kill your own grandfather, what then? When you come back, will you find yourself? Well, that is a question. But is it possible to travel through time? Well, to the future, maybe. But to the past, definitely not. Or at least we don't know it yet. I'm not saying that I believe that we can travel back in time, but anyway, nothing is impossible. And some people believe in multiverse. And that's actually our very next question. Do we live in a multiverse? This is coming next. Don't go anywhere. I'll be right back and talk about this very question. So do we live in a multiverse? And when scientists propose bold new theories, sometimes they open unexpected possibilities. So it has been for cosmology, which is the study of the origins and structure of the universe. Theories about the expansion of the early universe and about ways to reconcile gravity with other forces in physics have led to the possibility that we live in just one of an endless array of universes. The theory of cosmic inflation, which is first proposed by Alan Guth in 1980, solves some problems of Big Bang cosmology by positing that space-time expanded at an extraordinarily rapid rate in its early moments. Corollary theories say that although our universe stopped inflating, inflation elsewhere might continue, forming other universes like so many bubbles right next to our own bubble. String theory is an attempt to bridge the gap between relativistic physics and quantum physics. According to string theory, at a fundamental subatomic level, the universe has many more dimensions than the 4 we know. Other universes could have formed in this multi-dimensional space, invisible to us. Now, of course, the biggest problem in all these multi-universe theories is that they are unprovable, at least for now. We can't observe these other universes. We can only theorize they might be there, but we can't see them. But if it is true, there might be another you in another universe, but you'll never know. We'll never know. Well, it's good stuff for movies and for fiction, obviously, but who knows? That might be true. That might be proven one day, and you might meet yourself in another universe. Who knows? But that is definitely a mystery, and we still have 2 more to go, so don't go anywhere. Next, we're going to talk about dark energy. I'll be right back. So what is dark energy? If you jump into the air, gravity soon pulls you down again. But what if you kept rising faster and faster? This sort of logic-defying behavior is what astronomers are now seeing in our universe. Instead of slowing in its expansion as its mass drags on itself, the universe is accelerating. The source of this speed is still completely unknown. Scientists call it dark energy. Astronomers in the 1990s discovered the acceleration by measuring the distance to supernovae in remote galaxies and learning the stars were farther away than expected. The energy needed to power this acceleration is huge, representing roughly 70% of the substance of the universe. Theories about the nature of dark energy are vague and problematic. A quantum theory explanation suggests that the energy comes from virtual particles, popping in and out of existence, but the math doesn't seem to work. Perhaps, as Einstein once proposed, empty space has its own energy that increases as space increases, represented by a cosmological constant in the relativity equations. But obviously there's still no evidence for this, or we may simply be wrong about how gravity works, in which case there is no dark energy, but we seriously need to revise some basic physics that we so believe in. And this is possible, folks. This is one thing I like when I read mysteries. I don't like mysteries just because the idea that this is mysterious and this is just like we can put that in a movie or so. Of course, that is entertaining enough. The idea is that we can't accept everything so blindly. At least question these things we take for granted. Because sometimes you may figure out something new, not because you're the most intelligent person in the world, but maybe because you're the most curious person in the world. And you're here for a reason, right? You're as curious as I am, and you want to know about these mysteries. And there is one more before we wrap up this episode and this series, and this one is about the theory of everything. It will be our last mystery of our Great Mysteries series. So don't go anywhere, I'll be right back. So will we ever find the theory of everything? That's our last question. Well, the theory of everything is often described as the holy grail of physics. It's a grand term for a theory that would reconcile our current conflicting models of the physical world. The revolutionary physics of the 20th century left us with 2 ways of explaining nature. One is relativity, which describes the large-scale interactions of the universe, particularly the force of gravity, in terms of the geometry of space-time. The other is quantum physics, which explains the small-scale interactions of 3 other forces, electromagnetism and the strong and weak atomic forces, in terms of the exchange of particles. Unfortunately, the theories are incompatible. String theory is one attempt to bridge the gap. This complex and controversial theory, which is actually a group of theories, starts with the idea that fundamental practices are made from loops of string or membranes that vibrate in many dimensions. The tough mathematics of string theory applies to all the basic forces. String theory has its critics, though, who regard it as untestable and unscientific. Most scientists believe our physical theories will eventually come together. Physicist James Turfel once wrote, "Mature sciences don't grow by replacing one theory with another, but by incorporating old theories into new ones." So will we ever find this theory of everything? Maybe. Who knows? But until this very day, we still don't have this one theory that explains everything. And it's another mystery. And folks, I would like to thank you very much for listening to the entire series. And for those of you who are listening to this episode for the first time and you haven't listened yet to the other 5 episodes in the series, just go back and listen to the entire series, because the rest of the series is as interesting as today's episode, if not even more. And in every episode, I try to talk about a different topic. But with that, we come to the end of this series. And don't forget that you can find the transcript of this episode on my website, EnglishPlusPodcast.com. The link is in the show notes. Also, while you're on the website, check it out. See the many learning opportunities you can find there. With that being said, this is your host, Danny. Thank you very much for listening to the very last episode of our series, Great Mysteries. More series are coming along, so stay tuned. Until then, this is your host, Danny. Thank you again for listening. I will see you next time.